Thank you, Jesse. So just to add one thing which will help me explain. So the examples you see, what they generally have, so they define each of these two as separate clauses. So we have in this class we've spoken about these as rules as well. So I might say as something like this is a rule 1, a rule 2, a clause 1 and clause 2 interchangeably. That's the first thing. Secondly, each of these atoms like 3xy and qxy, so these are termed in the paper as subclauses. So when I say subclauses, I mean terms like this. So there can be more subclauses as an and to the, on the side, like that. And then obviously this is the head of a rule or head of the clause, and this is the body of a rule or body of the clause. Yeah. So what do they do? How do they do this? First they get the clauses, then they determine the ground atom which goes with each clause, then they introduce the weights, then they do inference, then they do then from the inference they minimize the error, which is the differentiable part, and then they go back and then again they change the weights and you know the how the machine learning thing goes. So first the clause search. So the objective is to find promising clauses that entail many positive examples, but only a few negative examples. So like as Jesse said that ideally we should give all the positive ones and none of the negative ones. But in this case, while we are searching for promising clauses, we relax it a bit. We are just focused on getting as many positive examples as possible. So we start with general clauses or strong clauses, which may entail many examples, but they may also include many negative examples. So the idea is to reduce the number of negative examples. So we iteratively specify or weaken those same clauses such that it entails less number of negative examples. This might end up entailing less number of positive examples as well, but we don't care for now. So how does this refinement work? So a refinement operator is this rho L of C, takes the clause as an input, and it can it does one of these four things and to give a weaker clause. So let's say we start with pxy, and these three are the three variables, and these two can be the two atoms. And the first thing it can do is this func, so which is application of function symbols. So we replace any variable with a function of the same variable or some different variable. In this case, let's say z. We can substitute constants, so we can substitute any of the variables with constants. We can replace variables with another variable, or we can add atoms like this. So we do some of these and we get a new set of clauses. So how do we do it? So remember this slide Jesse presented, we start with the same example. And then we start with this basic clause, which is px of y. These are two parameters. N beam says how wide in the beam search do we go, and E beam says how deep in the beam search do we go. And then we have beam search like this. So we start with the initial clause. We can generate these like with those functions I spoke about. And then we have an evaluation function like this, where for some reason the clause is an R, but basically this function returns a higher value if the particular clause returns a high number of, entails a high number of positive examples and a lower value otherwise. So we evaluate all of these clauses a particular depth. We pick 2 in this case, which gives the highest value, and then we further divide them or refine them. So now that we have the clauses, we do the next step, which is finding the ground atoms. So we have the clauses, we have the Q, which is the LP problem. Now we have something called the capital T, which is basically how many number of inference steps does the does this particular ILP do. So that's another parameter. And then the objective is to find the ground atoms for each clause in this clause set C. So finding G. So we start with let's say we have this new example which has this is the positive one positive example, one negative example, one initial fact, and this is the clause we start with. So we have just one clause and T equals 0. So we first initialize G with all the ground atoms which you can see on screen. So this and these three plus this is false and then this one is true. So that always goes into the ground atoms. And then we when we try to do the unification, which again Jesse spoke about. So we try to unify the head of the clause, which is the x square x, with some one round atom which we can find. So we pick ES to the power X to the power 6, 0, and we can unify if we replace X by this value. So we say this is an unifier. Now with this unifier, we evaluate the body of the clause, which is this EX, and then we get ES to the power 4, 0, and we add this to G. So G gets updated, E gets updated, so it gets reduced from 2 to 1. So we do it again till E becomes 0. So again we try to unify. We see we can unify this with this using S square 0, and then we add that to G. So now we get the set of ground. So the next step is the composition of the program. So for that we make a tensor. So the dimension would be C cross G cross B. You know C and G. What's B? B is basically the number of the maximum number of subclauses which can be there in all the clauses which are there in capital C. Basically. So what's each element of X? So sorry. Yeah. Right. So for clause I, round atom J, and for the subclause K, we put a particular value. What's the value? It will be the index of the round atom which we use to substitute that. That's what this first line means. I know it's confusing. I'll come to the explanation in a bit. What should be noted is that if we do not have that many subclauses, we just replace it by true, which makes sense because then we something ended with true is just that. And then if there is no unification possible for that round atom, then we just put false. That means it's a 0 essentially. And when I say index, what that means is that we had this set of round atoms, and if we write it like this, then we see each has an index associated. So essentially, this will return some number in that position of the matrix. Yeah. So now to understand how this goes, let's say we have these two clauses C0 and C1. Corresponding to that, we have X0 and X1. Starting with C0, it's a clause or it's a rule which has no body. So as long as X is not 0, it will or false, it will always be satisfied. So we see that when X is false here, the round atom is false, then we replace we put the index of 0, which is for false. For everything else, we put the index as 1, which is for true. So this is string. Same for false and true, it's always 0 and 1 here. For this part, we look at this one, where is S to the power 4, 0. So here is the ground atom. So if we put this in the body of the rule or the clause, what we get is S to the power 6, because S square plus S4, we get S to the power 6. So for this particular case, so that will come after this. So similarly, if you want the head to look like E S to the power 4, what we want to replace this EXY is S square of 0, which is here. So we put 4 here, which is corresponding to this one. Similarly, if you put X equals E0, we put here, because in the head of the rule we get ES power 0. So that's why we get 2 here. There is no unification possible for these two ground atoms, so we put it as false. So that's how we get this tensor. That's like really the key part of what we're trying to do. So now they say that there will be 6 number of clauses in the target program. So if the number of clauses are m, then we have m weights of 1 for each clause, and now each weight is now C dimension. So essentially, for each clause, we have a component of that weight vector corresponding to each of the promising clauses we had found. So you can imagine it this way that, okay, now, so if we have so that's like a probability of a particular clause being chosen for this one of these m clauses. So again, like this is, I'm saying clause and clause, so it might get confusing, but what I'm trying to say is that from the promising clauses set, which one do we choose for each of these m clauses? So for that, once we have the weights, we do the so we assume that the weights are ideal. Then if we take the softmax, we get the correct m clauses if you want. And so, as a result of doing it this way, we might actually end up with several clauses with the identical predicate. That's like the same atom in the head, and that's fine. You remember the Evans paper? They could only take pairs of clauses with identical predicates. That's what they improve on. We can have 3, 4, 10,000. That's completely fine. Also, we might end up having missing certain predicates altogether if this weights deem that they are not promising enough. Yes. So now that we know that, we try to do the inference. So this is the infer function. These are the inputs. So the unknown part is the V. So what V is basically a valuation function which maps ground atoms to their values at time capital T. So essentially, if the ground atoms are present or true or existent in the world at a particular time, then they will take the value 1, otherwise they will be 0. That's what T says, and T is just the time. So how do we compute F infer? So we first get this value, which is basically a function for the clause I for a particular time step. So valuation function corresponding to a particular time step and for a particular ground atom. And we do a logical AND. So this is a product, which essentially in the logical domain, it becomes a logical AND across the subclauses. And what does this gather function say? It's basically a mapping from the indexes, which we saw in the previous example. So we had like 0, 1, 2, 3, 4, 5, it could be anything. So we map from the indexes to the values in the valuation function, which means basically any index becomes either 0 or 1, and then we can take the logical AND. So once we have that, we do a weighted sum and to get this HL function, and then we do something called a soft OR, which is a function defined over all these value functions we got in the previous step to get this RDT. And they say that this is a smooth logical OR, and then this defined as such, and this is gamma is the smooth parameter. And because it's smooth, you can do the differentiation and updation, the back propagation and those kind of stuff. And then we want this F infer gives VT, right? So to get VT is inferred in an iterative manner. So from each time step, we go move to the next time step like this, and we get the next valuation function. And finally, we get this when small t equals capital T, then we say, okay, we are done. So how do we put this all together? How do we solve that? We started with this Q, it's the algae problem. So here we have all this stuff. So we generate atoms and label squares. So this Y is the label and E are the atoms. So this just says that the label will be 1 if it's part of the positive example and 0 otherwise. We do the conditional probability for each atom, and we know all these terms here already. And then we minimize the cross entropy loss. We have all done this in one or the other machine learning system. So we do that, and then as we continue iterating, the weights become better and better, and eventually we find what we want to find. So yeah, this is basically what we have been talking about. So I think we have, all of this. I have 1 minute left over for my personal time. So you can look at this and see if it makes sense. Basically, the minimization part happens in the red part, which we can differentiate and update stuff. And then the individual parts, which are what they have come up with, like the beam search and the enumeration of the facts, tensors, weights, all of that is the main part. And then they combine in this lots of arrows here. So, how they combine.